Hello and welcome back. The subject of today's video is going to be torque. Torque is the rotational analogy of force. So in the linear world, remember to change the state of motion of an object, to change the state of linear motion of the object, you need an unbalanced force. So remember Newton's second law. It said that the sum of all of the forces acting on an object will be equal to the product of the object's mass times its resultant acceleration. So if we add all of these forces together and we get 0, then there will be no acceleration, or there will be no change in the state of motion of the object. It will remain in a state of equilibrium. If instead we sum all the forces together and we don't get 0, then we will have an acceleration for the object. So Newton's second law can be written in the rotational world using torque as the rotational analogy of force. So first of all, let's introduce the symbol for torque. So torque gets the symbol tau. It's a letter from the Greek alphabet, and torque is a vector quantity. So I can write then that the sum of all of the torques acting on an object will be equal to that object's analogy to mass in the rotational world, and that's called rotational inertia, I, times its angular acceleration, alpha. So I is equal to rotational inertia and alpha is equal to rotational or angular acceleration. So tau is the symbol we use for torque. If we add up all of the torques, and again they have to be added vectorially because torque is a vector, then the sum of all of those torques will be equal to the product of the rotational inertia of the object times the angular acceleration. Angular acceleration gets the symbol alpha, is also a vector quantity. It has a magnitude and a direction. So let's define what torque is specifically. So torque is a vector, and to calculate the torque exerted by a force, and every force may or may not exert a torque, we will need to be calculating each and every one of them. The torque exerted by a force is going to be equal to a new type of way of multiplying vectors called a cross product. R is the distance from the axes of rotation, or from your summing point, to where the force is being applied. And the force F, of course, is the force. And this X right here is called a cross product. So this is called a cross or vector product. Has a very easy way of figuring out the magnitude and direction part of it. And we just need to get comfortable with how to do that. So first of all, the magnitude part of the torque is going to be equal to the distance from the axes of rotation to the point of application of the force. And that's going to be the distance r times the force F. So it's the magnitude of the first vector times the magnitude of the second vector times the sine of the angle in between the vectors. So theta equals the angle between R and F. R is equal to the distance from axes of rotation or potential rotation. Sometimes you won't have rotation, but you want to see if possibly you could have rotation. You would pick a point to sum about. To point of application of F. Okay, so F then of course is the force, and we know the magnitude part of the torque, so this is magnitude of torque. What about the direction part of the torque? The direction part of the torque comes from the right-hand rule. So the right-hand rule, which we will abbreviate as RHR, yields the direction part of torque. Okay, so let's look at an example of how that happens. So let's say we have a door. So this is our door, and these are the hinges of the door. So these are the hinges. And so the door handle is out here somewhere. And imagine that we are going to apply a force to the door handle. We're going to try and open up this door. The axis of rotation of the door is this dotted line that goes through the hinges. So this is the axes of rotation. That's these axes about which the door rotates. And so let's say we're going to exert a force into the glass or into the board, okay? So we're going to grab this door handle and we're going to exert a force in. When we're designating into and out of, in other words, we're including a third dimension. The board creates two dimensions, but if we want to add a third dimension, then we can show these directions as an X or a dot. An X means that it is into. A dot means it is out of. So if I draw an X for the direction that I'm applying my force at this point, then that means I'm applying it into the board. If instead I draw it as a dot, that means I'm pulling, I'm exerting that force out of the board. So this allows us to include a third dimension. So now we can draw the vector R because we're going to be applying this force here at the door. So let's go ahead and draw the door over here so that we don't clutter up anything. And remember, R is the distance from the axis of rotation to the point of contact of the force. So the vector R is drawn with a tail at the axis of rotation and a tip at the point of application of the force. So that is our vector R. The force we're applying is into the board in this particular example. The right-hand rule is the following. You use your right hand. That's why it's called the right-hand rule. And you place your right hand completely straightened out in the direction of the first vector that's in your cross product. So we look at our cross product and we see the first vector that's in our cross product is R. So we put our hand in the direction of the first vector. Notice if R instead pointed the other way, then I would be putting my hand in this direction. If R pointed out of the board, then I would be putting my hand in this direction. If R pointed away from the board, I'd be putting my hand in this direction. So you start off putting your entire hand in the direction of the first vector. So R pointing to the right, my right hand now points to the right. Now I want to rotate my hand, my right hand, keeping it pointing to the right until I can flip my fingers into the direction of the second vector. So your fingers only bend in one direction. So the second vector is F. F is into the board. The only way I can flip my fingers into the board is if I have my palm facing toward the board. So I can flip my fingers into the board as you see there. So now I've got my right hand pointing to the right, my fingers now flipping into the direction of the second vector. Then when I extend my thumb, that gives me the direction of the resultant vector, which in this case is the torque. So the torque is straight up. And notice that that is in the same direction as the axes of rotation. So remember, this is the axes of rotation. The resultant torque here is going to be in the upward direction. So that's the direction for the torque. So this is how the right-hand rule is applied. Okay? And I'll just write it down here. So for the right-hand rule, right hand straightened in direction of R. Then rotate right hand until fingers can bend into F's direction. Then thumb extended yields torque's direction. So torque is a vector. Now we see that we can calculate how large the torque exerted by a force is by taking the magnitude of the first vector, that's the distance from the axis of rotation to the point of application of the force, times the magnitude of the second vector, that's how large the force that's being applied there is, times the sine of the angle in between the force and the vector r, between r and f. So this provides us the magnitude part of the torque. The direction part of the torque comes from applying the right-hand rule. So the right-hand rule is placing your right hand straightened in the direction of the first vector, r. Then rotate the right hand until the fingers can bend into F's direction. Then your thumb extended yields the torque's direction. We'll have some time to practice with this as we move on. And in the next video, we'll talk a little bit more about rotational inertia, and we'll look at summing up some torques as well. So we'll see you next time.